Hi there, folks. Today we're looking at indirect proofs, all right? And the idea behind indirect proofs is kind of like process of elimination, all right? It's essentially what indirect proofs are, all right? So indirect reasoning, all possibilities are considered and all but one are proven false. Essentially, with indirect proofs, we don't prove the thing we want true by directly going to that thing and saying, hey, I'm going to show that this is true. I show that everything else is false, so then by default, that thing has to be true. Again, it's that idea of process of elimination, all right? Indirect proofs or indirect reasoning, we eliminate the possibilities, all right? So we essentially just say, hey, this is false, this is false, this is false. The only thing is left is this, so this thing must be true. That's indirect reasoning, all right? And that's kind of the idea behind indirect proofs. So the basis for this is showing that things are false, all right? And if all these things are false, what I have left has to be true, all right? The idea of showing that things are false is this idea of using contradictions, okay? And we've kind of run into this kind of a while ago when we started talking about logic and reasoning, but contradictions are just statements that can't be true together, all right? Two things that directly contradict one another are two things that cannot be true at the same time. They can't be true simultaneously. All right. And so that's the idea here is if we're trying to prove something indirectly, I have to show that everything else is false. I do that by making contradictions. Okay. And then once all the contradictions add up to all these things being false, whatever I'm left with is the thing that has to be true by process of elimination. That's the idea behind indirect proofs. Okay. So let's talk about contradictions first. Let's make sure we're understanding which things are contradictory or how to make a contradiction. And so here, when I identify the statements that are contradictory, I'm just going to label these, I'll call it A, Statement B, and Statement C. And I just want to say, hey, which of these would be contradictions? So we've got figure A is a square, all right? Figure A is a quadrilateral. That means it has four sides. Figure A is a triangle, all right? So if I were to look at these and say, okay, which statements would be contradictions? Well, the first one and the last one would be a contradiction. So A and B together would be contradictions because can something be a square and a triangle at the same time? Well, no, a square has four sides, a triangle has three sides. That's impossible, okay? Likewise, B and C would also be contradictions. And B and C would also be contradictions because B is saying, hey, it's got four sides, and C is essentially saying it has three sides. That's impossible. Those things can't coexist. And so I have two sets of contradictions here. A and B would be a contradiction. B and C would be a contradiction. And so if I was doing an indirect proof, and I had the statement that figure A was a square, and then later what I did proved or showed that figure A was a triangle, well, that would be a contradiction, which means whatever I started with must not be right. I started with something that was false, with something that wasn't true, which leads to a contradiction, okay? Likewise, if I look at these guys, once again, let me label them as A, B, and C. So I've got segment AB is parallel to segment XY. I've got segment AB is congruent to segment XY, and I've got segment AB is perpendicular to segment XY. And so I have to decide which of these things would be contradictions. Can they exist together? So if I looked at like those two segments being parallel versus those two segments being congruent, could they be congruent and parallel at the same time? Could I have two congruent segments that are parallel? And the answer is yes. I can think about how that would look. I could draw that thing, all right? But that's possible for them to exist together, all right? If I looked at something like B and C, could I have the congruent segments and have the lines be perpendicular? Well, yeah, I could take two congruent segments and make them perpendicular, and we could visualize what that would look like. Even that perpendicular symbol looks like two congruent segments that are perpendicular, okay? And so those things can exist together. What I can have is I can't have two lines that are parallel but also perpendicular, okay? Those are kind of opposing opposites. Parallel means they never intersect. Perpendicular means they intersect at a 90-degree angle. So A and C this time, those would be contradictions, okay? Those two things cannot happen at the same time. If I look at these guys, it says, again, I'll label it as A, B, and C for my statements. So it says triangle ABC is acute. That means that all the angles inside are acute angles. I think we've talked about that in the past. Triangle ABC is scalene. That means none of the sides are the same length. All right, so all the sides have different lengths. And triangle ABC is equiangular, which means all the angles are the same. Okay. And so this one is maybe a little tricky. So if I started, let's start with some of the obvious ones. All right, something like equiangular. Equiangular means they're all the same angle. We know stuff about triangles where they're all the same angle. All right. If I were to draw an equiangular triangle, they're all 60 degrees automatically. I should have drawn that a little bigger so that I had some space to write. Let me try again. So here's an equiangular triangle. They're all 60 degrees automatically, right? To make all the angles the same. Well, if I look at that, that's an acute triangle, all right? All the angles inside there are acute. So A and C exist together, all right? So then I have to branch out a little bit. Let's talk about a scalene triangle. Maybe I could draw a scalene triangle. So trying to draw a scalene triangle where they all have slightly different angles here. Okay, so I draw something like this. They all have slightly different angles. Again, I should have gone a little bit bigger. But I'm just kind of warping this thing a little bit and saying, hey, you know what? Let me change this a little bit. I'll make this angle a little bit bigger, and I'll make this one a little bit smaller. Okay, so maybe this one is a 50-degree angle, and maybe this one's a 40-degree angle, and now this one's a 60-degree angle. And see, those still add up to 180, so this triangle exists. It's an acute triangle, and it's scalene, all right? I drew three sides that weren't the same length, okay? And so that's possible. The thing that's not possible is, remember, we know some special things about equiangular triangles. If I jump back to this one, equiangular triangles are automatically equilateral, meaning all the sides are the same, okay? And we had that as one of the theorems that we did way back when. So this is equilateral. Well, could it be equilateral and scalene? Could all the sides be congruent, but all the sides not be congruent at the same time? And so those are the contradictions here. All right. And it wasn't maybe obvious. If I had written equilateral here instead of equiangular, it would be very obvious. Okay. But we had to take this a step further and say, okay, I know if it's equiangular, I know it's equilateral. That can't be, that's impossible if it's also scalene. Okay. So B and C are the contradictions here. Okay. So now let's dive into an indirect proof. An indirect proof starts with basically assuming the opposite of whatever we have. So assume the negation of what is to be proven, all right? And then what we do is we kind of roll with that assumption, all right? We assume the opposite of the proof statement is true, and then we start doing the proof as if that thing is true, and we just continue the proof until we get to something that's a contradiction, till we get to something that can't be possible based on the given, all right? And as soon as we get to that point, what we have, once we have a contradiction, we can say, you know what? If there's a contradiction here, then what I assumed must be false. And since I assumed the opposite, then the opposite must be true, okay? So if I assume the opposite of the proof statement and I end up getting a contradiction, well, my assumption is false, which means the opposite thing must be true. By process of elimination, the thing I assumed is false, the thing that I should have done must be true. Okay, so that's our last step of this thing. We conclude that the assumption is false and that the original conclusion must be true. Okay, again, if I get a contradiction, it means whatever I started with is false. Okay, and if what I started with is false, then the other option has to be the thing that's correct, okay? It's process of elimination, all right? I've always called these the George Costanza proofs, for anyone who's ever seen Seinfeld, all right? He goes through this predicament where nothing he does works, so he decides, you know what? If every instinct I have is wrong, then the opposite must be right. So he starts doing the opposite and things start working out for him. And so that's the idea here, is we're doing the opposite of this thing and it ends up being false. Well, it means the other thing must be true, okay? If the opposite is false, then the original must be true. That's the idea behind indirect proofs, okay? We assume the opposite, we get a contradiction, which means the thing we assumed is false, the opposite must be true, okay? For example, if I look at something like this guy, it says given triangle ACB is scalene, all right? Scalene means none of the sides are congruent, all right? None of the sides are the same, all right? I want to prove that angle A, angle B, and angle C are all different. They all have different measurements, okay? And I'm going to approach this kind of like a paragraph proof. And so as I look at this thing, the thing I want to do is I want to assume the opposite of what it's telling me to prove. Okay, I want to prove that A, B, and C are all different measurements. So let's assume that they're not. Let's assume that A and B are the same. Okay, so I'm going to assume, and this is what I do here. I just write, hey, I'm going to assume that angle A is congruent to angle B. And we could do this as a two-column proof as well. So if I assume that A is congruent to B, let me draw a picture over here. So here's A and B. I'm assuming that those are congruent. So right away, if I assume that those are congruent, I can conclude that triangle ACB, instead of going to triangle ACB, I just want to say that AC is congruent to BC. Right? I'm going to say that these are congruent. That's a theorem that we have. I'm going to say that AC, oh, sorry, I switched colors again. I'm going to say that AC is congruent to BC. And that's because if the base angles are congruent, the opposite sides are congruent. Okay? And see, I can say that because that's a theorem we had. We had a theorem when we dealt with isosceles triangles. And, I could go this route now. I could say, hey, if those are congruent, well, this is a triangle ABC is an isosceles triangle. And it's isosceles because that's the definition of an isosceles triangle. And so right away, I didn't necessarily have to include that triangle ABC as an isosceles triangle step, but that's a contradiction. Can a triangle be scalene and have all different sides and isosceles at the same time? All right, and have the two sides that are the same? And the answer is no. That's a contradiction. All right. So I would just say this contradicts the given, because the given is absolute truth. That's the thing that has to be true. This contradicts the given. Therefore, I use these three little dots for therefore. Angle A does not equal, or is not congruent to, angle B. Okay, because the thing that I'm allowed to say now is the opposite of the assumption I made. And notice here that I did not deal with C at all. Okay, I have to show that all of these have different measurements. So then what I would do is I would do this same proof again. Okay, I would do this same thing again, but I would assume that A is congruent to C this time. Okay, and then I would have to do it again, and I would assume, that angle B is congruent to angle C. Because really, I have to show that none of these are the same, all right? But you see that the next two, I'm not going to write these out, all right? The next two would be the same. So I'm just going to put a dot, dot, dot here, all right? It's the exact same proof. Angle A, is not congruent. I didn't write that up here. Just put a slash through it to show that it's not congruent. Not congruent to angle C. And then likewise, this one, same thing. I would do the identical proof one more time. And so collectively, what I'm doing is showing that none of these are the same, okay? I'm eliminating all of the options, okay? I want to prove that none of those angles are the same. The only other option would be some of those angles being the same. And so if I can show that none of those angles are the same, then I can go from here. I could have also assumed that all three of them are the same. All right, I could have approached it that way, and then show that all three of them can't be the same, that kind of thing. All right, but again, that's a little bit trickier. In terms of this thing, it's better to individualize. But again, all we're trying to do is assume the opposite of what we want to prove, show that that's wrong, which means the opposite, the thing we started with, has to be right. Okay. And so after I do this, if I did it a couple times, I can now say that A, B, and C all have different measures. Okay? I've shown that it's not possible, all right, if they have equal measures, it's not possible to go without contradicting the given. Therefore, the opposite must be true. They can't be the same. Okay? If I take a look at this next one, it says given that M is not parallel to L, again, that's what that little slash means, just means not that thing. I want to prove that angle 2 is not congruent to angle 6. And, you could try doing this indirect proof as a two-column proof. But again, it's a little bit wonky to do it that way, so it's easier just to do it as a paragraph proof, okay? And we always just start with our assumption. So for this one, I'm going to assume, so let me go a little bit lower. I'm going to assume the opposite of what it's telling me to prove. It wants me to show that angle 2 is not congruent to angle 6, so I'm going to assume that angle 2 is congruent to angle 6. So angle 2 is congruent to angle 6. Okay, that's my assumption. All right, so that's step 1. All right, now let's see what I can show. If based on the fact that I'm saying angle 2 is congruent to angle 6, what do I know about these things? All right, and right away, I know that the lines must be parallel. Okay, so I can immediately say that M is parallel to L because, well, look at what I have. I have corresponding angles that are congruent. If corresponding angles are congruent, then the lines have to be parallel. Okay? So right away, I assumed that those were congruent. Congruent corresponding angles means the lines are parallel. Well, that directly contradicts my given. So now I would say, hey, that contradicts the given. Therefore, again, I use these 3 dots means therefore. Therefore, the thing I assumed must be false. The opposite must be true. Angle 2 is not congruent to angle 6. Okay? So again, I make an assumption. I show that that assumption is false so that I can assume the opposite, so I can show that the opposite is true. Okay? That's the idea behind indirect proofs. All right? We're assuming the opposite of what we want to prove. We've run into a contradiction, which means the thing we assumed is false. All right? The original statement must be true. Okay?